All right, welcome back again, everybody. Today we're going to be continuing with Chapter 10. We're going to be doing Section 10.2, which is where we finally get to do some calculus with the parametric curves we were talking about last time. So I'll pull up the slides and let's get started. There we go. Okay. Oh, wait, let me do this too. There we go. All right. Okay, so here's the overview. Well, I should say the big idea is this. The last section, we described what parametric curves were using parametric equations, and we got access to all of these much, much more interesting curves, right? All sorts of crazy looking curves. You can define them in all sorts of crazy ways. Well, now we want to be able to do calculus with these things, with and on these things. I think I say that in the next slide. Anyway, so we're going to talk about tangents and concavity. We're going to talk about areas, arc lengths, and then surface areas. So that's the overview for today. All right. Yeah, exactly. I thought I had just said something. I thought I was going to say this. Now that we have this new way of describing curves, we want to be able to do calculus on them and with them. Like if we have a parametrically defined curve, it'd be nice to, find tangents at a point or find area under a curve or arc length, the length of a curve given parametrically, right? We'd like to do all those types of things. So far, everything that we've learned and everything you've learned in calculus before can be generalized to parametric curves using a third parameter, t or something. What's also cool is that we can recover all of our previous formulas by using the basic parameterization for a Cartesian curve. Or I should say a curve defined by Cartesian coordinates. Or not even that, I should say not Cartesian coordinates, but using like a Cartesian parameter, where x is the input and f of x gives you the output. So what I'm saying is, when we have these generalized formulas, we can always recover the particular formula when we have this parameterization, which is kind of cute. And we'll see that in just a few minutes. Okay, so starting with tangents and concavity, the basic idea is that we want to be able to find tangent lines to parametric curves. So how do we do it? Well, let's start with our parametric equations for x and y, where f and g are differentiable functions. If we want to talk about derivatives, we need to be able to talk about we need differentiable curves, differentiable functions. We're going to make another supposition here, and this is a subtle thing, but it is necessary for what we talk about in this section. We're also going to assume that y is a differentiable function of x, all right? So we're assuming that each of these are differentiable functions of t, and that this is also a differentiable function of x. And hold on one second here. Seems like I'm getting a little bit of, hold on just one moment. All right, hopefully that fixed it. I was just seeing some flashes in one of my video feeds here. Uh, I still see it again. Might have to pause and try this again. But anyway, I'll try to just push through it. So we're going to suppose that y is also a differentiable function of x. So in other words, that we could write y as a function of x and that that function would be differentiable in terms of x. This isn't too far-fetched of a result because kind of like I had mentioned in the last section, if we've got a parametric curve, we can decompose it into a whole bunch of individual curves that are functions of x. It's just that can be very painful, and oftentimes we don't want to have to do that. So this assumption is subtle, but it's not really asking too much. Not really asking too much. If you want me to discuss more, please ask me about it, and we can go into some more detail about it. But because y is also a differentiable function of x, the chain rule gives this result right here, that dy dt is equal to dy dx times dx dt. That's just the chain rule. Now, as long as dx dt is not equal to 0, then we can divide both sides of this equation by dx dt. And what we get is that dy dx is equal to dy dt divided by dx dt. So this is kind of a cute result. This actually gives us the slope of the tangent line. So one thing I want to point out is that dy dx is still dy dx, like you remember it from Calc 1. It's the slope of the tangent line, right? And this is saying that if you want to find the slope of the tangent line, you do dy dt and divide by dx dt. So in kind of a symbolic way, it's kind of like taking dy dx, right? And multiplying the top by 1 over dt and and the bottom by 1 over dt. It's kind of a cute result there. All right. Yeah, hold on one more second. Hold on a second here. Okay. All right. So back to what I was saying. Yeah, so this is just the formula for the slope of the tangent line when your curve is given by parametric equations. So some things that we can get from this right away. The tangent line will be horizontal when this is equal to 0, but this will be equal to 0 when the numerator is equal to 0. So in particular, when dy dt is equal to 0, provided that dx dt is not equal to 0 at that point. So you can't divide by 0. The tangent line will be vertical when the denominator is equal to 0. So that's when dx dt is equal to 0, again, provided that dy dt is not also equal to 0 at that point. So now we can find vertical and horizontal tangent lines, and the process is basically the same as what you saw in the past. Now, if both dx dt and dy dt are equal to 0, or if y can't be written as a differentiable function of x, then you've got to use other methods to find tangents to parametric curves. All right, got to use other methods. So we're making some assumptions about our curves. All right, so that was for tangents. Now, how do we find concavity? So we can calculate concavity, or sorry, we can investigate concavity by using the second derivative. So if you remember from Calc 1, if you want to determine where a curve is concave up or concave down, you use the second derivative, and the second derivative will tell you that. Sorry, hold on, the flashing is getting to me. Okay, tried something else, so hopefully that will work this time. All right, so back to concavity. Remember that this is the second derivative, d squared y dx squared. Um, Leibniz notation is really handy because it lets you talk about the difference between the differential operator and the derivative itself. So remember that this symbol right here, ddx, that's the differential operator. That's the function that says to take the derivative of something. So how did we calculate a second derivative? We would differentiate the first derivative. dy dx is the first derivative, right? So by the definition of this differential operator, we can do this, or we can write things this way. This is a little bit subtle, and it's a little bit confusing, so if you need me to clarify, don't hesitate to ask. But this is the formula we had from the previous slide, the formula for the tangent line. Remember that dy dx is equal to the derivative of y. So this is showing you that this symbol is equal to this symbol right here. So dy dx is taking y and differentiating it. Similarly, dy dt is like taking y and differentiating it with respect to t. So this is equal to this, and this is equal to this. And the reason that I've written it this way is because now you can see where y is coming into play, right? So what we're now going to do is, if we want to find the second derivative, we're going to do this, right? So what we're going to do is we're going to replace y with dy dx. And that's what's happening here. So how do you compute the second derivative? You basically just, you do this instead. You're going to differentiate dy dx with respect to t, and then it's all going to be over dx dt. And that's what gives us this formula right here. Okay, so let me try to summarize everything here. The first derivative is given by this formula, dy dt over dx dt. The second derivative is given by this formula. So this says to differentiate your first derivative with respect to t, and then divide it by dx dt. So in particular, you're not redifferentiating the function x. You're not redifferentiating x. All right, so this is how it works. Again, I know that's a bit confusing. I'm more than happy to explain more during the activities. Don't hesitate to ask. But in fact, maybe I'll do this right now. Let me just throw up the thinker, and you should just ponder how this is giving us this. This connection is where we're getting the formula for the second derivative of a parametric curve. All right, moving along. Let's try an example here. So let's say that we have a curve that's defined by the equations x equals t squared and y equals t to the fifth minus 4t. So we're going to do a few things. We're going to show that this curve has two tangent lines at the point 2 comma 0, and we're going to find their equations. We're going to find the equations of those two tangent lines. We're also going to find the values of t where the tangent line is horizontal and where it's vertical. We're going to determine the intervals of concavity, where it's concave up and where it's concave down. And then we're going to sketch the curve. All right, here we go. First step. Now, so remember part A was show that there are two tangents, right? So this says show that there are two tangent lines at the point 2 comma 0. Well, if you're at the point 2 comma 0, that means that x is equal to 2 and y is equal to 0. But just looking at this first relationship, if x is equal to 2, that means that t squared is equal to 2, and so that means that we get two results for t, plus or minus square root of 2. Remember, whenever you take a square root, you must include a plus minus. You must include a plus minus. So this tells us that there are two different times where we cross the point 2 comma 0, which is exactly what we had to show. So that means there will be two tangent lines at two different times. All right, now if we want to find the slope of those tangent lines, or just the slope of the tangent line anywhere, we use that formula for dy dx right here, this one. Okay, so what is dx dt? Let me clear some of this junk out. What is dx dt? Oops. Differentiate that with respect to t, and you get 2t. What is dy dt? Differentiate this with respect to t, and you get this. So now we've got dx dt, we've got dy dt, so that means dy dx is just the ratio of those two results. All right, so this right here, that is the slope of the tangent line to the curve at any time t. Notice it's with respect to t, so at any time t, we've got it. All right, now we want to define the equations of the two tangent lines at the point 2 comma 0. That was the next part of the question, right? Yeah, find their equations of the tangent lines. So here we go. We're going to take our formula, dy dx, and we're going to substitute the two values of t. So we're going to plug in t equals negative root 2. We get this, and when you simplify, you get this. So that is the slope of the tangent line to the curve when t equals negative root 2. Do the same thing for positive root 2. You get a calculation, pretty similar, and you get 4 root 2. So this is the slope of the tangent line to the curve when t equals positive root 2. So now that we've got the slopes of the tangent lines and we have the point where these tangent lines occur, we can get the equations. Those are the equations of the tangent lines at that point. Cool, not too bad, right? Just kind of another formula, and then the rest is the calculus you remember from Calc 1. All right, now let's find when it's horizontal, when the tangent line is horizontal and when the tangent line is vertical. So remember, the tangent line will be horizontal when the numerator is equal to 0, because this is a rational function. So when the numerator is equal to 0, we're going to get a horizontal tangent line. Set the numerator equal to 0, solve for t, and you get those two values. So at these two times t, you'll have a horizontal tangent line. To find the vertical tangent lines, you set the denominator equal to 0, and you're just going to get t equals 0. So at time 0, you have a vertical tangent line. Right. Next part. Now we want to talk about concavity. So to find the second derivative, we're going to use that formula for the second derivative. And remember that formula said you're going to differentiate the first derivative with respect to t. And we're going to leave the denominator here alone. So we've got a whole function here that we're differentiating with respect to t. In my case, I used the quotient rule and got that once I differentiated, and then I simplified, and then simplified further. So this formula right here is the formula for our second derivative. Let's see. The numerator is actually always positive, so that's not going to affect the concavity. Because remember, the concavity, I shouldn't say it won't affect it. We want to look for, how do I say this? If we want to know if something's concave up or down, we want to look for the sign of the second derivative. Well, the sign of the numerator is always positive, but the sign of the denominator changes when t is equal to 0 because you have a cubic down here. So at time 0, the denominator will be 0. But then when your time is positive, t will be positive. So this will be positive, which means this will be positive, so you'll be concave up. And then when t is negative, this will be negative. So this whole thing will be negative and it'll be concave down. So what this is saying is that the concavity changes at time 0, and it's concave up afterward and concave down before. 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 All right. And now here's the picture. So this is what the curve looks like. You can see how t changes. So the curve is actually being generated like so. All right. We can also see those tangent lines. So notice that there is a vertical tangent line right here. This is when t is equal to 0. So at this point, that's when t is equal to 0. And what did we say? We said that before, what was it? After, yeah, okay. So before t equals 0, the curve is concave down. Where is it? I'll just do this. There we go. So when t is negative, the curve's concave down, which makes sense because when t is negative, we're looking at this part of the curve and it's concave down. Then when t turns positive, it's concave up. Notice we also have two tangent lines that are horizontal right here and right here. This is when t equals negative fourth root of, oh geez, I forget what it was, 4/5. 4/5. And then this here is when t equals positive fourth root of 4/5. We also have those two distinct tangent lines at the point 2 comma 0. So here's the point 2 comma 0, and we had one tangent line with a negative slope, and we had one tangent line with a positive slope. So there are the two distinct tangent lines. So this is pretty cool because with these formulas, you can do all of this analysis that we've been doing for this whole class and your previous class, right? You can still do that with these types of curves. All right, so that's tangents and concavity. Now let's talk about areas. So let's say that we have y, which is a function of x, so that we can write y of x, and let c be the curve that it represents. So this is something we've seen in the past. This is just the standard parameterization of a function of x. The area under this curve is given by the usual area formula, right? Just the integral. So take the integral of that function from a to b, you get the area under the curve. Now let's instead suppose that c can be described by parametric equations, x equals f of t, y equals g of t, and that the curve is traversed once as t goes from alpha to beta. So how can we take this result and get a result for our parametrically defined curve? Here's how it goes. So first, notice that the derivative of f with respect to t is dx dt, so we can rewrite dx as f prime of t dt. Why do we need that? Because in this area formula, dx appears over there. That's the differential, differentiating with respect to x. Now we can talk about differentiating with respect to t. So our differential is going to change from dx to f prime dt. Next, we're essentially doing a substitution, right? We're essentially substituting something in, as you'll see. We're substituting for y and we're substituting for dx. So when t is equal to alpha, y is going to be equal to a, which is g of alpha. And when t is equal to beta, y is going to be g of beta, which is b. Thus, by the substitution rule, just the good old substitution rule, use substitution, we get this. So we replaced y with g of t. We replaced our bounds with the appropriate conversions, and we replaced dx with f prime of t dt. So this is the area formula for a curve that's defined parametrically. All right. Yes, here we go. So one little note, because this is something that a student asked me about a couple years ago. So it turns out that if your terminal point is actually the leftmost endpoint, then the bounds of integration alpha and beta are switched. So right now what we're assuming is that our initial point is over here and that our terminal point is over here, right? And the curve is traversed this way. What this little note is saying is, hey, if your terminal point is actually over here instead, so instead of this being IP, it's TP, and your initial point is over here, if you have this scenario where the curve is being traversed in reverse, am I doing that? Wait, this way, in reverse. So instead of going from left to right, you're going from right to left, then these bounds are going to be switched. So you've got to ask yourself which way you're traveling, basically. So if you're traveling backward, then the bounds of integration have to be switched to accommodate for that. Why does that work that way? That's because when you integrate with respect to x, it happens in the positive x direction. This is kind of a subtle point about the Riemann integral. The Riemann integral is a directed integral. So the integral scans from left to right. But if you're reading backward, then your integral gives you the opposite result, right? So you might remember from Calc 1 that if you switch the bounds of integration, then it changes the sign of the integral, right? So that's what's happening here. This is basically saying that if you end up going in reverse, then you need to switch the order of the bounds to preserve the equality there. All right. So let's try this one. This is a fun one. So let's find the area under one arch of the cycloid that we saw in the previous section. So the cycloid is given by these formulas. X equals, let me use green here. X equals this, and Y equals this. Just like so. Those are the formulas for the cycloid. We're going to find the area under one arch. So here we go. For one, r is a constant. I should probably say that. R is a constant. It is not a variable. R is the radius of that circle that rolls, right? It's constant. What's changing here is theta. Theta changes, and so that means that x and y both change. One arch of the cycloid is traversed between 0 and 2 pi because that amounts to one full rotation of the circle. So when the bicycle wheel rolls once, it'll have traced out 2 pi radians. So using the substitution rule above, we know that dx d theta is this, so we can write dx as this. I had to pause for a minute there because I was like, wait, is this dx d theta? Let me check. Let me check for a minute. If I differentiate this with respect to theta, I get 1 minus cosine theta. Yes, okay. There we go. So there's dx. And we already have a formula for y. Y is equal to this. And so now we can use that formula. Here we go. So what is the area? The area is the integral from 0 to 2 pi r, which I'll talk about in just a minute, y dx. Right. Now, why is the upper bound 2 pi r? Well, I'll say this. The reason the upper bound is 2 pi r now is because we're integrating with respect to x. And the circumference of a circle of radius r is 2 pi r. So remember that the circumference is 2 pi times the radius. So as that bicycle wheel rolls along, it'll trace out one whole circumference in 2 pi radians. But remember, its radius is r. So if we're thinking in terms of x and we're thinking in terms of horizontal displacement, then we're going to integrate from 0 to 2 pi r instead. Now when we do our substitution, things are going to change. So when we do our substitution, the upper bound just becomes 2 pi, right? Because what was our, becomes 2 pi, wait, I don't have it on here. Where is it? Right here. I guess I didn't include this, but I will say, okay, maybe I can do it real quick. So when, oh geez, what is it? Theta. Okay. No, I don't know if I want to take the time to do it. Maybe I'll leave this for you to do, actually. This is something you could think about and ponder. So see if you can figure out why the bounds are changing from that to that. And the reason is really just because of the substitution. So take a minute, think about it, and then try to work that calculation out on your own. There you go. Try to work that out on your own for a minute, and then we'll move forward. All right, here we go. After doing our substitutions, this is what our integral looks like. Now we can simplify things a little bit. Remember, r is a constant. We've got two factors of r, so we can pull out an r squared. And then we end up with 1 minus cosine theta squared. Now you're going to just FOIL everything out, distribute, and you get this trinomial here. You can use the power reducing identity to get that reduced. And now you can use fundamental theorem of calculus, compute the antiderivatives, evaluate at the endpoints. And when you do that and take the difference, you'll get this expression, which simplifies to 3 pi r squared. 3 pi r squared. So that's the area under one of those cycloid curves. So this area right here, this is 2 pi r. The area here is 3 pi r squared. Cool stuff. All right. Oh yeah, so this is a good motivating reason for why we like parametric equations and parametric curves and frankly different coordinate systems, which we're going to talk about in the next section and the section after that. The Cartesian equation of just 1/2 of one of these arches, so not even the full arch, but I mean 1/2 of that full arch, just 1/2, like literally from here to there. The Cartesian equation for that is this formula. That's the Cartesian equation for it. And as you can see, it's extraordinarily messy. And you got to ask yourself, would you like to integrate that? Or sorry, dy. Would you like to integrate that? And hopefully you're like me, and the answer is like no. I really would not like to if I could avoid it. And that's why we have these nice parametric equations. So sometimes your parametric equations are better at describing the curve, and then they make it easier to do calculus on the curve as well. So you don't want to have to be stuck with just Cartesian equations. All right, just a little motivation for why we like these things. Okay, so now we talked about areas. Let's talk about arc length. And this is kind of a cute result. We already saw this derivation once before, so it's going to look very familiar. In 8.1, we derived the formula for the length of a curve given by this function here. Excuse me. So this is just the standard parameterization where the vertical displacement is given by, or the vertical position is given by the horizontal displacement. So using a similar argument to the one we saw before, we can derive the formula for parametric curves. I won't dwell on this too long, but I want to show you what it looks like so you can see how all the pieces come back. And again, it's a good point to remind you that you really do want to understand the mechanics of the Riemann integral. You want to understand those mechanics. So this time we're going to divide the time interval alpha beta into n subintervals, t sub I minus 1 to t. Now, in each one of these subintervals, each one of those subintervals corresponds to two other subintervals, a subinterval in terms of x in the range of the function x, and a subinterval y in terms of, a subinterval in terms of y in the range of y. Again, that's because our parametric equations are functions of t, right? So if we talk about this time interval, it corresponds to two other intervals in terms of x and in terms of y. That's all I'm trying to say. All right, now let's go back to this picture. This picture will look very familiar. How did we figure out what to integrate? We found the lengths of all of these approximating line segments. We're going to do exactly that same process again. What is the length? The length is given by the Pythagorean theorem. These differences are delta xi and delta yi. Notice now both delta x and delta y need to be indexed by I. It depends on the interval, right? So they're not uniform. They're different. The only one that is uniform is the time interval. This one. That's the one that's uniform. The time interval is uniform in length, not the x and y intervals. All right, so you get these. We're going to multiply by delta t over delta t. That's the clever one. We're going to move that inside the, or sorry, move the bottom piece inside the radical, and then we distribute it to each term. We get that. And then simplifying a bit, we get this and this. And lo and behold, we get this approximation. So the length of the actual curve is approximately the sum of all these approximate lengths, which is given by this formula. Now we can take the limit as n goes to infinity and produce the length as delta t goes to 0, and we produce the exact length, which looks like this. And here's the formula. So this is the arc length formula. This is really, really cool. So notice the formula is pretty much the same as the formula we saw before, but now instead of having a 1 here and a dy dx here, we've got dx dt and dy dt. So that is the more general formula. This is the general formula for the length of a curve given by parametric equations, right? Here it is written with Lagrange's notation instead of Leibniz notation. And then altogether we have this. So this is the formula. Here's the theorem. That's pretty much it. Here's the differential that we get, ds, right there. And then now let's see a cute result. All right, here we go. Let's recover the formula that we got in section 8.1. Let's recover it. So let our parameterization be this. So let x be t, and then y is equal to f of t. And now because x is equal to t, alpha is equal to a and beta is equal to b, because they're the same, right? Now, when we differentiate this with respect to t, we get that dx is equal to dt. So using our new formula, we can sub in what we have here and we get this. Dt is dx, dt is dx, dt is dx. Well, dx divided by dx is 1, and 1 squared is 1, so this becomes 1. And then here we have dy dx still, and so voila. We get the arc length formula that we derived back in section 8.1. Ta-da! I think that's kind of cool. I think that's cool. Okay, so there's the arc length formula. Now we're trucking along. We're almost done. We've got the general arc length formula. We've got the arc length formula for Cartesian equations. Now we can talk about surface area. And I can hear you all like groaning, even though I can't see you. The good news is you already have all of this background. You already have all of this background. And if you were paying close attention to the mechanics of the integral, it's just these same formulas over and over again. So that's why those details are important. The mechanics are important. So what is the formula for a surface area? A surface area of rotation, right? Surface area of a solid of revolution. Sorry, that's what this is for. It's going to be this. And what is this formula? It's adding up 2 pi r L, right? 2 pi r L, 2 pi r L, except now in this case, L is given by those, or given by that differential, which is determined by those parametric equations. So again, you barely have anything to remember as long as you remember how the integral is constructed. Okay, all right. That's it for this section. So I'm glad it was a little bit shorter. So let's play. I hope you like the activities from a couple of these sections. There's a really, really cool question on this activity, so I'm excited to get to it. But I'll go ahead and stop there. Thank you all again very much, and I'll see you next time.